Today we'll look at electric fields, and similar to a gravitational field, due to a mass which pulls other masses towards it, charge creates an electric field that attracts or repels other charges. And here is an example where we have charge A being a positive charge, which creates an electric field that radiates away from it. So therefore, we can obtain the electric field using the Coulomb force by dividing by the test charge B. So what we have is the Coulomb force over the test charge. And this test charge can be any charge in general, so we'll just call it charge Q. And this test charge Q is some charge that's going to be placed in the electric field of A. So it can be anything. And therefore the electric field of A is independent of the test charge. Now suppose that charge A is plus Q, then the electric field of charge A can be written as Q on 4 pi epsilon naught by 1 over r squared. And now if we place some test charge in the electric field of A, and supposing it has a magnitude of 3Q, and it's a negative test charge, then the Coulomb force on that test charge, due to its presence in the electric field of A, is effectively minus 3Q multiplied by EA, which is effectively Q by minus 3Q over 4 pi by the vacuum permittivity by r squared, where r is going to be the distance between these charges, but specifically from charge A to charge B. And therefore, because we've got a negative result here, then the Coulomb force on charge B is going to be attractive. So the positive is going to attract negative charges. Whereas in contrast, if this charge were positive, then you'd get a repulsive force. Now in contrast, if we looked at a negative charge, the electric field vectors would point towards it. And another observation we can make is that the electric field is denser near the charge. So where the lines are denser, the electric field is stronger. And where the lines become less dense, you get a weaker electric field, due to this inverse r squared proportionality. And I'll see you in the next video.